Now, we're actually running out of time. I didn't think this was going to take so long, but the other thing I want to show you is something called, it's called a fine grain reduction. And I start the counter again. Although actually, yeah, when we get to 12:55, it'll be 25 minutes. I'm just going to check that it's recording, because otherwise, yeah, it's 38 seconds. Okay, so one of the hot topics in complexity theory are these things called fine grain reductions. And what this means is that you can show things we assume are hard, really, really hard. You can show that if they are really, really hard, then you can't do something in subquadratic time. So the big one, the really famous one, is edit distance. So so there's something called the strong exponential time hypothesis. I think this is hyphenated, or at least it should be. Maybe it isn't usually. So this is known to its friends as Seth. Okay? So, what does the strong exponential time hypothesis say? We cannot solve in 2 to the, I think I'm getting this right. I think it says minus epsilon time for epsilon, constant epsilon, positive constant epsilon. And this, of course, is in the worst case. Where n is the number of variables. Okay? So obviously you can solve SAT in something like 2 to the n time, where n is the number of variables, because you just check every possible truth assignment. There are, how many of them are there? There are 2 to the n. Each variable is either true or false. Okay, but Seth says you can't do this in 2 to the n minus epsilon. Okay? So, is that clear? So that's saying that SAT is really, really hard. There's nothing that really beats the naive approach of just try everything. Or not by, I mean, yeah, maybe you can shave something like a log or a polylog factor off. So this is talking about SAT and stuff that takes exponential time, well, super polynomial time. This is saying that it takes exponential time. Okay. So, people showed that if Seth is true, I'm not sure people actually call it Seth. I've heard it said, but it's definitely written Seth, but maybe they say S-E-T-H. Seth is easier. So, okay, if Seth is true, people have shown that you can't do, okay, so this was a theorem by Abud and Indik, I think. So there are a bunch of people working on this. They're like Brinkman and Vasilevska-Williams, and but I think it was Amir Abud and No, maybe I'm getting confused. I have to look up who actually. I think it was Indic and something. But they showed that, so theorem, if Seth is true, then we can't solve edit distance. In n to the 2 minus epsilon time. Right? So you can't, so this is called strongly subquadratic. So it says that you can shave off like log factors, polylog factors, but you can't do, in the worst case, you can't solve edit distance. The edit distance we know. The edit distance we know how to solve in quadratic time because I forgot to reset this, but it doesn't matter. We saw how to solve it in quadratic time. Now we also saw banded dynamic programming, which actually in practice does better than quadratic time, because we're computing the edit distance of two similar strings. But in the worst case, for years and years, people didn't find anything subquadratic, and this sort of explains, well, we're unlikely to, if Seth is true, then there isn't a subquadratic algorithm. So Seth is a stronger hypothesis than just P is not equal to NP. P could be different than NP, but you could still have something that was like 1.5 to the N or something like that. So Seth is saying P is not equal to NP, and SAT is pretty much as hard as we think it is. There is nothing much better at SAT. If Seth is true, then you can't get a much better algorithm for edit distance that works in the worst case. Okay? And I'm going to prove this. I'm not going to exactly prove this to you. I'm going to show you one of these reductions from something that ties together a polynomial time problem and an exponential time problem. Something that we know how to do in polynomial time to something that we don't know how to do in polynomial time. Okay? Questions? So this is kind of cool because you get lower bounds for problems that we can do in polynomial time, but we would like to do faster, and we prove them on the basis of things we believe about problems we can't do in polynomial time, or at least we think we can't, assuming P is not equal to NP. Okay. And I'm going to try to do this in 17 minutes. Do I still have students? Oh, I've lost a couple of people. Okay, so I'm not going to show you the reduction from SAT to edit distance because I don't know it offhand. I should have looked it up last night, but I was trying to write the lecture notes. So some of the lecture notes are I'm catching up very slowly. Okay, so what I'm going to reduce to is, let me see if I'm getting it. I'm going to reduce SAT maybe I'm going to reduce 3 SAT. Yeah, I think I'm going to reduce 3 SAT to a problem called orthogonal vectors. Okay. So orthogonal vectors, you're given for orthogonal vectors so we're given 2 sets of vectors. Say they're d-dimensional, and two sets A and B of d-dimensional vectors. D is going to be pretty small. Okay, and we're going to assume binary. Okay, so for example, maybe you get 0, 1, 0, 0, 0, 1, 1, 1, 0, 0, 1, 1. And you get 1, 0, 0, 1, 0, 1, 1, 1, 1, and 0, 0, 0, 0. Right, okay. So I'm not saying that they have to be distinct. Okay, so this is A and this is B. Now, we can do this in, assuming D is not very big. Let's assume that D is like polylogarithmic in the number of vectors in these two sets. Then the question is there a vector in A and a vector in B that are orthogonal? That is, their dot product is 0. And there it is. For example, 0, 1, 0 and 1, 0, 0. If you take the dot product of those two vectors, it's 0. Those two vectors are orthogonal. Okay? Clear? Anybody? Still there? Okay, how long would it take us to do this? Assuming, ignore D for the moment, like it's small, it's polylogarithmic. All right, roughly, how long would this take? Could you write an algorithm that does this in polynomial time? So let's say that there's n vectors in A, I'm not going to say n, I'm going to say m. M vectors in A and m vectors in B. How long is this? How long would it take? Nope. Just to tell me, can you pick a vector in A and a vector in B such that those two, a vector V sub A in A and a vector V sub B in B such that V sub A dot V sub B equals 0. So they're orthogonal. Just to find, yes, right? You check every vector in A and every vector in V, and like you do this pairwise thing. How long does the dot product take? It takes you like time D, but I told you to ignore D because D is small. So orthogonal vectors is basically quadratic time, right? You can do m times m, right? Easy. Okay. So how can I reduce 3-set to orthogonal vectors? 3-set is hard, and orthogonal vectors is easy. Well, the key thing is, this is not going to, so I started teaching this because in 2019, somebody in the class said, do reductions always have to take polynomial time? And I said, no. All the reductions you normally see in third year take polynomial time. But technically, this works because the reduction takes exponential time. Okay. Can we optimize that? That's the key thing. That's what we're going to talk about. We're going to show that if Seth is true, you can't do better than quadratic time for orthogonal vectors. Right? It's easy. Somebody just came up with the algorithm for solving orthogonal vectors in roughly quadratic time. We're going to see that if SAT is as hard as we think it is, then that's about the best you can do. That's kind of cool. It ties together like SAT, which is like something far away and really hard that you don't want to work on, and orthogonal vectors, which is something easy and which you can do in polynomial time. Okay, so So remember, we cannot solve SAT. We're saying that SAT takes, you can't do it in 2 to the n minus epsilon. I have to remember, I hope I get this right, and I hope I can do this in 10 minutes. It's not actually a hard proof. I'm just going to make sure that this thing is recording again. Okay, so maybe I should tell people who are confused about this NP stuff not to watch this lecture, because it's just seeing an exponential time reduction is just going to confuse people. But if you're understanding this, given a 3-sat formula F, with n variables, we split, and let's say n is even, okay? Say n is even. We split the variables into 2 groups. Right? With n over 2 variables each. Okay? So we're going to call these variables, we're going to call these things group X and 2 groups X and Y. Okay? So they have n over 2 variables for each of them. Now, what we're going to do is take the variables in group X and consider all the possible truth assignments to those n over 2 variables. All of them. Okay? So how many are there? 2 to the n over 2. Right? And the same thing for y. All the truth assignments to variables in y. Now, what we're going to do is for each of those truth assignments, we're going to write a vector. Okay? For each of these truths. So now this is the sneaky bit. For each clause, so for a truth assignment, tau to variables in X, compute which of the clauses are made true by tau. We write a vector v sub tau saying which of the clauses is made true by tau. Now, some of the clauses tau will not satisfy, right? Because it only, tau is only talking about half the variables. So it satisfies a clause if for example, that clause contains x10 and tau x, x is okay. It contains variable z10 and tau x contains z10 and tau says it's true. Then tau satisfies that clause and we write that in the vector, okay? And, or if there are 2 to the n over 2 taus for x and 2 to the n over 2 taus for the other n over 2 variables, right? So the sneaky thing is, when we write these vectors, when we write the vector v tau for tau, if tau satisfies the ith clause, makes the ith clause true, regardless of what the truth assignment to y, then we don't write a 1, right? You would automatically think 0 is false and 1 is true. That's not what we're going to do now. We write, if it makes it true, we write a 0. And if it makes it false, or if it makes it false, if it doesn't satisfy it, that is, maybe it assign, maybe there's a variable in there which is not in x, so it doesn't make the variable. So if it's like z10 or z15 or not z27, and z10 and z15 are in x, but tau makes these both false and z27 is in y, then this tau doesn't satisfy this. Maybe you could still set z27 to satisfy it, but tau by itself is not enough. Now, if tau says z10 is true, then great, tau satisfies this and you write a 0. If tau doesn't satisfy this by itself, you write a 1. Okay? So, I should have come up, in the lecture notes, I'm actually going to use this as, I'm going to come up with I'm actually going to write the SAT formula for the 3-SAT formula from the other day. So, I have 3 minutes, so I'm just going to say this. Okay, so you end up with, well, no, okay, I'm not just going to say this. I'm going to erase this. Okay. So, we get 2 sets of 2 to the n over 2 vectors of length k. This is number of clauses. But how big is k? How big can k be? Well, it's not that big because there are only n variables, so there are 2n, not 2 to the n, 2n literals, and then you can, for each clause, you choose 3 things. You choose 3 literals, right? So it's like k can be at most 2n, choose 3, which is like 2n cubed. So it's something like n cubed, so it's polynomial in n, whereas these sets are exponential in n. So the dimension of the vectors is really small. We're just going to ignore that, right? So suppose you have these 2 sets of vectors. Suppose that 2 of them are orthogonal. I have like 1 minute. Suppose that 2 of them are orthogonal. Now, what does that mean? That means that for every component, for every I, But for every I, so remember the i's, the components of the vectors are the clauses. Either the ith component is 0 in the vector from A, which means that the truth assignment to x satisfies that clause, or it's 0 in the vector from B, which means the truth assignment to y makes this 0. So how much time does it take us to build these two sets of vectors? I'm over time, sorry. Well, this is only going to take, to generate these vectors, it's going to take about 2 to the n over 2 time, right, times 2. And then, so if we can figure out, if we could say, are there any of these vectors that that are orthogonal, then there would be a satisfying truth assignment, because we would say, oh, well, then we take the tau to x that gives us this vector from A, and we take the whatever tau, the truth assignment to y that gives us this vector, and then when you put them together, every clause is satisfied, because either it's 0 in the vector from A, every component, which is a clause, is either 0 in the vector from A or 0 in the vector from B, or both. If neither truth assignment satisfies a clause, then it's 1 in, then we put a 1 for that clause in both vectors, and the dot product of 1 and the product of 1 and 1 is a 1. So the total dot product is not 0. The two vectors are not orthogonal, right? So we can take this formula of sat and we can turn it into these two sets in time, like 2 to the n over 2, so roughly. We can turn it into these two sets of vectors such that if two of those vectors are orthogonal, then there is a satisfying truth assignment. Okay, so if we could do this so this, we're going to say this is not 2 to the n minus 2 anymore. We're just going to call this m. If we could do this in better than m squared time, say we could do this in m to the 2 minus epsilon, then what would that mean? We could solve sat in, well, now we're going to call this again, we're going to change m back to 2 to the n over 2 minus to the 2 minus epsilon. And what is this? This is 2 to the n, and this is like minus 2 times epsilon times 2, just times something. Yeah, okay. So I'm actually getting something minus epsilon times n over 2. Well, this is 2 minus epsilon, 2 n. I'm over time. Look, I correct. But do you see how this goes, my 10 remaining students? You can work this out, and you could, if you do this, maybe I stated Seth, so if you do this, you say, okay, if we could get a subquadratic algorithm for set, for orthogonal vectors, it would mean that by turning sat into an instance of orthogonal vectors, we could solve sat in better than 2 to the n, better than 2 to the n time. Now, the key thing is, this reduction is not a polynomial time reduction, because how long we're taking a formula that's like size n, and we're turning it into two things of size 2 to the n over 2. It's an exponential time reduction. But this ties together, this says, if sat is as hard as we think it is, then orthogonal vectors you can't do in subquadratic time. And that, nobody was really, like, that's weird.